Hello, my dear students, and welcome to our first lecture in our chemistry course for the spring semester of 2003. I've decided to do this first formal coverage of course material as a screencast. So, first of all, I'd like to welcome you to my iPad, but you will be seeing me frequently in other formats as we go along. You actually won't see me today, but if you look at the brief introduction video, you will see my face there. So, what I want to do is, if I can, open up a file here with my Apple Pencil that I transferred over. Let's perhaps try it here if I can. And there's the file in the middle of it, but it's not. Let's see. I can't see the whole. Yeah, I can't see the whole slide here. So let me get out of this and try something else. Here is open our view for today in PowerPoint. I will go ahead and make this PowerPoint available as a PowerPoint, but of course it won't have the voiceover annotations. I just realized, though, that since the last time I taught this course and provided online notes, PowerPoint has converted to a subscription service, and it's probably looking for a subscription. So I will get out of this because I don't want people to realize how slow my internet is. And let's try something that works. Look at this. It came right up. Actually, it came up on the last slide. But what I want to do today is test my Apple Pencil out. And let's see if we can do this a page at a time. So this is not from your book. It's from a book I've used when I've taught this very same course for PCCUA. In fact, just last year, Zoomdoll and Zoomdoll, a very classic introductory first-year chemistry book, as is your Brown and LeMay that's listed in the syllabus, though I only got that out of the previous instructor's syllabus and have not confirmed that with the bookstore. In the meantime, I will make this, as I will make all of my lecture notes and presentations, available in our Blackboard classroom shell. And I will also post a book from a website, you'll hear about it from time to time, called I'll think of its name and I'll post the website. It's got every chemistry book for every chemistry course you'll ever want to take online for free from top drawer universities. The one I picked this last time was from the University of California system. I think it was UC, not Santa Barbara, much further north, UC Davis, I believe. And the chemistry textbook they've written and are using there. There's a wonderful open source website called Chem Libre. There's really any need to ever buy a chemistry book ever again for any student anytime in their life. But this particular presentation is titled Chapter R because it's a review chapter and a brief introduction to chemistry. And I just want to get something posted before we do a deep dive into our course, get everybody settled, everybody registered, our late registrants caught up, and really attack the subject later this week or next week. So I want to review just briefly some of the terminology and the things we need as we work through chemistry, and that is specifically units of measurement, a brief discussion of accuracy and precision, or dealing with uncertainty, and a very important topic and an obligatory topic, and that is significant figures. When I post this, you will see these other aspects which we will get into as we get to them. So we may come back to this, but this is all I want to cover today. So I left a break in your subject matter, and oh my gosh, there is a purple line there. And we'll cover these three topics very quickly. And I'll try to write once in a while to show you that this is an interactive presentation. Now, I want to make it as quick as possible, so I'm going to talk fast. Chemistry is a quantitative science. We often need to measure the amounts of chemicals, the amount of a toxic chemical like lead in the water in Flint, Michigan, or the amount of a product we make. In my history, for example, how much adipic acid, which you don't know this, but it's 1/2 of nylon. It's a moderately expensive feedstock chemical that is made from relatively inexpensive syngas and, more importantly, petroleum. And so, we want to know how much petroleum to buy, how much is going to react. We want to know how much product we're going to make, because what? We want to know how much something costs, and we want to know how much money we're going to make. So measurement is an important part of chemistry. When you go to the doctor and they draw some blood, they're going to measure potassium and sodium ions and the presence of different proteins and the amount of glucose in your blood. And so there will be quantitative measurements dealing with chemistry all the time. And that is something that turns a lot of people off about chemistry, and yet it's an integral part to our science. So anytime we make an observation, we need two parts: a number or a value or a scale, and then the actual scalar itself. They call it a scale, or the units, because you can't just say I have 20. 20 what? Atoms, molecules, ions, grams, or milliliters. It could be weight, volume, or all different kinds of units as you report a number. So we've given you some examples. How many grams? Here's a different unit: joules, seconds. And so we are going to be using 5 primary units from the SI system. The SI here stands for Système International, French. You need to say that with a French accent. And it's the French abbreviation for the International System of, basically we're going with IUPAC rules. IUPAC stands for the International Union of Pure and Applied Chemistry, and there are 5 basic units in the SI system. And those are the kilogram for measurements of mass, not weight. Weight is a force. Take physical science to learn about that. Length, the basic unit is the meter. Time, where the basic unit is the second. Temperature, where the basic unit is the Kelvin. We're not supposed to say degree Kelvin anymore, but a Kelvin is equal to a degree Celsius, and personally, despite what the books frequently do, I was taught to write Kelvins with a capital K because it's named after Lord Kelvin and is a person's name. I guess the ampere would be too, so you can do that. And you see people use different abbreviations. It's a capital A. Some people just abbreviate it to amp, but the official abbreviation is a capital A, and the amount of substance present, the mole. And we'll be covering a lot of the mole concept in chemistry. We don't get much of an abbreviation for the mole because little m is already used for meters, and capital M is an abbreviation for mass, and MO is an abbreviation for the element molybdenum. So I guess the best we get is one letter off when we abbreviate it. Every other unit is derived from these. Notice there's nothing there for volume. No liters or milliliters or fluid ounces or gallons or things we use to measure volume with. And that is because those are what we call derived units, as opposed to these 6 fundamental units. And so these fundamental units can give us all the other units. For example, if I want the volume of a cube, it would be the length times the width times the height. And if I do that in, for example, meters, I would end up with a value where the length in meters, the width in meters, times the height in meters would give me some value in cubic meters, which is a volume measurement. Okay? And you can convert that if you were doing centimeters, but I don't want to talk about centimeters yet because I've talked about the prefixes or the prefixes. Now, one of the problems people have with chemistry is the scope of chemistry, because we're working with things, atoms, that are very, very small, almost unimaginably small, and conceptually that's very difficult. And the other problem people have is we work with numbers that are absolutely enormous as well as incredibly unimaginably small. For example, if you talk about how many molecules there are in just a swallow of water, or about 18 milliliters, you will find that there are around over 10 to the 23rd molecules of water in a good-sized swallow of water. That's unimaginable, because right here we only go up to 10 to the 18th. But you've heard some of these more common multipliers or prefixes or prefaces. The prefix deca and hecto are not used very commonly, but you've heard kilo and mega. Certainly kilo with kilograms or kilometers when measuring distance, or kilograms when measuring mass. Also, if you buy and study computers at all, you've heard of giga and tera when you buy your flash drives or jump drives, or a computer with so much RAM or so much memory, or a hard drive with so much storage. You know, most people today are talking gigabytes of RAM and terabytes of storage, although, you know, it's only going up. So you should know the more common ones shown in blue. We're going to use them, and I'm not going to redefine them as I use them when we talk about chemistry. If we get smaller and do fractional amounts, deciliters, centiliters, milliliters, centimeters, micrometers, nanometers, these are terms we need all the time. Deci, not so much, but those in the medical field will use a term called a deciliter, which, if you remember ever hearing about values for different things in your blood, for example, blood glucose is supposed to be kept below 100. 100 what? And it's a quantity per deciliter, which is 1/10 of a liter, or 100 milliliters That's a significant amount of blood. Because in the old days, to make these measurements, our tests weren't very sensitive, and they would draw 100 milliliters of blood, and do their measurements then. We can now do the measurements in a drop, but the standard values are still reported in deciliters for blood and in the medical community. Centi is 1/100th, 0.01, or what? 10 to the minus 2, and we'll be using these two systems for writing fractional numbers, both the decimal and the exponential or scientific exponent or powers of 10 form. And as you'll see in just a minute, there's a very good reason why we do this. So, centimeters. If you look at a yardstick, there's 100 centimeters in it, and centimeter rulers are very common. Then milliliters, and milli means 1/1000th, or 10 to the minus 3, 1 over 1,000. And you've all heard of a milliliter. If you look on your drink, whatever you're drinking, it will probably give you its volume in milliliters. Like I said, a good-sized swallow is about 18 milliliters. And it's a very common prefix used when we want to say 1/1000th. Micro means 1/1,000,000th, okay? So, if you notice, after the first two, they go in thousandths. So, micro means 1/1,000,000th. A micrometer is 1/1,000,000th of a meter. It's a very handy dimension when talking about cells. For example, a human red blood cell, I think, is 10 to 100 micrometers across. The average cell is. A bacterial cell is about, for E. coli, 1/2 micrometers. So it's a very common dimension term for expressing dimensions at microscopic level. Of course, we can't see atoms in a microscope, and when we do measure the distances or the sizes of atoms, we need to go down to nanometers. There is an archaic term called an angstrom, which I'll talk about when we get to bond lengths, and I'll talk about why it's handy. It's 10 to the minus 10th meters. Some people, especially particle physicists and people who work with subatomic particles or very high energy waves and the like, big energy, small space, quantum mechanical chemist and physicist, will use these terms as well, pico, femto, and atto, but they're outside the realm of our discussions in this introductory class. So, just briefly, I want to talk to you about accuracy and precision. Very often when we measure something, we estimate some aspects of what we're measuring. And a measurement always has some degree of uncertainty and is never probably as precise as it could be or frequently as precise as we want it to be. So we record all the digits we know with certainty and the first uncertain digit. So the last digit in a measurement or a value is uncertain. A good example is, let's see if I can expand this. There we go. Is this burette. Now it's red because it's dispensing liquid from top to bottom instead of bottom to top. But if you look at this, they've changed it because here it's under the 20 line and here it's above the 20 line. But if you look at this, this is 20. Then the next line here, if I can get a finer line, is 20.1, that line right there. And this line is 20.2. And of course, way down here would be 21. If I look at this and consider this, what do I say? Do I say 20.1 or 20.2? Well, one thing I can do is I can say 20.1 and a little more. And that last digit is uncertain. Is it about a half? Is it around 0.4? It looks like a little less than half, so I would say 20.14. This example here is giving us 20.15. And in our example, sorry, but when I save this, it doesn't look like Keynote likes the PowerPoint formatting. They're trying to say we have three digits, the 20.1 that we can read with great certainty, and then an uncertain digit that we kind of just do our best to estimate. So it's called an uncertain digit. And we'll get back to those when we talk about significant figures. Let me briefly describe accuracy and precision. Accuracy is how close you are to the true value. How accurate are you? Did you hit the mark? Precision refers to how your measurements agree. If you read this measurement, make this measurement, this weight, measure this volume, measure this frequency, measure this distance between atoms or between anything, multiple times, how much does your data bounce around? And we like to, oops, it's not going on to my next slide. We like to, see if I can move along, maybe there, not there. Now it's at least responding to me. We like to use this drawing. Oops, I didn't mean to go that way. Let's see if I can go back now. We like to use something like this, or a trash can with people throwing paper at it or something. If you throw with great precision and your throw is consistent and precise, it may not be accurate, you see a good grouping of your values and your results. If you are very accurate, you come close to the accepted value. Accurate, precise. Actually, this is accurate and precise. You could get this same value. If you're trying to, get an average, you may get things all over the place that when averaged out, do that. There's the old joke about, three people go hunting and they're shooting at a rabbit and one shoots too high, and one shoots too low, and the third person's a statistician and takes the average and says, got it. So, that's just something we're going to talk about and deal with when we do our labs and our quantitative problem solving in chemistry. Now, because that last digit is not significant, we can't report any beyond that. And you would be foolish to report something beyond that. But some people try, or the point at which insignificant, non-significant figures in a value come into play is frequently when they're calculated or derived, especially when someone gets two or three digit numbers and divides one into the other in the calculator and ends up with a value that says, 6.93473256774. We call that calculator vomit. If you started out with 2 3-digit numbers, you can only report the first three numbers, not all that other stuff. It is not significant. The assumption is if you write a number down and report it, in a scientific paper or in a textbook or in your lab reports or in your problem-solving forays into chemistry, it will be significant. So if it's a number, we make the assumption that it is always significant. If there are zeros preceding the number, these do not count as significant. Okay? So point in the example here, 0.048 has two significant figures. If the zero is between non-zero digits, of course, that zero is significant. So 16.07 or 10.67, wherever the zero lies between these digits, those would have four significant figures. Trailing zeros, we make the assumption if they're after the decimal point are significant. So you do not report them if they are not. So if you read it, we assume it's been properly vetted as a number, and those digits within the number are, those figures within the number are all significant. 150 only has two significant figures. You know, it's plus or minus 10. The last number, as we talked about earlier, is the number that is an uncertain number. It's the estimate, okay? If I want to say, how much is there? 150. Because I'm counting out screws or nails or bolts, and it's about 150. I might be right. But if I'm counting out, money or something, that I want more precision. So if I'm counting out something very precisely for military specifications, or it's money or something important or high value or just something that I'm counting because I'm counting it, I'm not counting it by handfuls, and there's on average 10 in every handful. So here's 15 handfuls. That's about 150 bolts. Okay? Could be anywhere from 140 to 160. So this digit is uncertain. But if I count out 150 important bolts and I want 150, not 149 and not 151, and it makes a difference, I need a decimal point. Okay? So they're significant only if the number contains a decimal point. And of course, if I were to write, let me go back there. If I were to write 150, sorry for my poor writing here, 0.0, in this case, I have four significant figures as I've reported it. And it means that I can tell the difference between 150 and 149.9, and I can tell the difference at this position between 150 and 150.1 or 151. It means I have certainty in these three digits, and the only uncertainty is here, but that I can tell and measure the difference between them. Exact numbers have an infinite number of significant figures. For example, if I count to 9, that is $9.000000 if it's $9. So it's infinite. There are some conversions that are perfect. For example, 1 inch equals 2.54 centimeters. You may or may not remember that from math, but it's 2.54000000 on forever. And so if it's a counting number, for example, that's the most common example, it is infinite number of significant figures, and this becomes important when we are doing calculations. Now, as I talked about, we're frequently going to use scientific notation. This has a great advantage. If you have a number in scientific notation, instead of writing 3,000, I'll use a different example. You write 3.0 .000 times 10 to the third, then the assumption is you can tell the difference between 3.000 and 2.999. Or you can tell the difference between 3.000 and 3.001 in this position. So this has 4 SigFigs, 4 significant figures. And this one only has 1 SigFig. Because we don't know if we were counting, like I said, by handfuls of grains of sand. What would be 1,000? I could put a handful in. And I'm just putting 3 handfuls into a bucket. And there's about 1,000 in a handful, 1,000 grains in a handful. So I don't know if I have 2,000 or 3,000 or 4,000, so I only have 1 significant figure. So this is the advantage. If you are writing your units in scientific notation, you immediately know your number of significant figures. Of course, the other advantage is when I'm dealing with incredible numbers, like I said, 10 to the 23rd molecules of water or H2O in a swallow, I don't want to write 1 followed by 23 zeros. That would take me forever to write out. I can't even get there. I don't even have enough room. So my point is, we need to use exponential, or what we call scientific notation. And if you have a TI-84 calculator, which you don't need for this course, but if you have it from your algebra course or anything else, I can teach you how to force it into or go back and forth between decimal notation and scientific notation in another lecture when we work problems or might use a calculator. Okay, so what happens for significant figures? Here's the actual rule. The significant figures in your result can only be the same as the number in the least precise measurement. So if you have 1.342 and even on, and you multiply it by 5.5 in your calculator, you may get a number of numbers. It'd probably be 7.3810. But you can't report that. You can't have 4 SigFigs because your least significant number only had 2 significant figures. And that means your answer must also have 2 significant figures. These other numbers in the calculator's answer are not significant. So, this might be, each of these weighs or has on average, 1.342, and I do 5.5 of them. That's the best I can do. So I multiply 5.5 times 1.342. And so now I can't go any more accurately than 7.4. I grew up in Europe, and I was taught to round to the nearest even number. When you are working problems, I will always give you plus or minus 1 significant figure. But I know in America they tend to just always round up. So when it's a 0.5, exactly. For addition and subtraction, the same thing. For any mathematical operation, your significant figures in your answer must be the same as your least precise measurement. So this has, 2 significant figures past the decimal point. And, use the decimal places for examples like this. And so that means my answer can only have 2 past the decimal point. I can add up the larger numbers, the ordinal numbers. And as you can see, we're almost done. Just think about this, and then I'm going to assign, when I post this, a quick exercise with some questions that I will also go over before I ask those questions again on a test. I'm going to give you a quick exercise on practicing significant figures. For things like measurements, we'll wait for the lab to practice accuracy and precision determinations. But we will be talking about significant figures throughout the whole course. So, here are two graduated cylinders, a 5 mil graduated cylinder and a 1 mil graduated cylinder, which is much more precise. And you can see, if I were to add these together, this one I would read as 2.9 milliliters, maybe a little over 2.91. You can 2.92. You can do that insignificant, but look at this one. This one is 0.2, and each one of these lines is 2. So 2, 4, 6, 8. 0.28. It's not quite to the 9. 0.28. It looks like it's almost perfectly on the line. Oh, a little beyond it. 0.281. And I have 3 significant figures past the decimal. And over here, 2. And let's see what they say. You know, they're saying here I have 2.9. And really, this is 2.2, 2.4, 2.2, 2.4, 2.6, 2.8. So I'm sorry. I said that was 2.91. It's 2.8. And almost maybe a little more, but the best I could do would be 2.8. I'm sorry, I was counting those lines as ones instead of twos. And here I have 2.81. So if I add this up, what am I going to get? Well, I'm going to get 2.8 plus 2.28 and a little more. And that would be, what, 3.081, which we're going to round to the fact that I only have 2 significant figures and a 2.08. Even though I have a very accurate measurement over here, I have a less accurate one here to 2 significant figures. I need an answer of 3.1. So that kind of concludes a quick introduction to scientific measurements, units, metric prefixes, and significant figures, the kind of obligatory introduction to chemistry. Please don't be scared. We're going to use math as a tool, but I'm not going to overemphasize the math. We're going to emphasize chemical principles, the study of matter, and the reactions it undergoes. So it will get better. In the meantime, check in on our Blackboard shell regularly, daily preferably, and keep up with your assignments. I'll post an assignment with this. And until then, until I post another lecture, summary, some demonstrations, and some other things, please stay safe. You will notice, too, if I might add one thing before I go, that I've provided video links rather than embedding the videos into our course shell. That takes you to my YouTube channel. I used to have hundreds of videos and many different things in there, excuse me, which I lost, but I've added a few things back. You may want to go ahead and follow me. It's at Dr. Mark Shanley, Dr. Mark Shanley on YouTube. is my channel, and you'll see some other videos which give you some more ideas of some of the things we're going to be doing. But I will post the specific ones you're responsible for as I make new ones specifically for this course. Goodbye now.